Hi guys, and welcome to Lesson 8, where we're going to talk about three different kinds of random variables that every probabilist should know: the Bernoulli, binomial, and Poisson random variables. The first of these is the Bernoulli. It's the simplest one. We run one experiment, and that experiment will succeed with probability p, and so therefore fails with probability 1 minus p. So p is going to be a number between 0 and 1, since it's a probability, and we usually talk about it as the probability of a success. And we say that x has the Bernoulli distribution with parameter p if the probability that x equals 1 is p and the probability x equals 0 is 1 minus p. So x is the number of experiments that have been successful. So we either had one successful experiment or 0 successful experiments. That's all there is to say about the Bernoulli. Oh, the expected value. The expected value of x is going to be 1 times p plus 0 times 1 minus p, or just p. So you could think of our experiment as we flip a coin, and the success is heads. So there's a 1/2 chance of getting heads, so p equals 1/2. And the expected value of the number of heads we're going to get is then 1/2. So it's just actually p itself. Okay, so the binomial is taking that Bernoulli, except for we want to run n experiments. And the outcome of each of the experiments is independent of the outcomes of the other experiments. Now you could think of it as flipping a coin 5 times. We're still looking at a heads as a success. So n is the number of trials, and p is the probability of a success for a given trial. And all of the trials have the same success probability. As in flipping a coin, every time it's a heads with probability 1/2, the success probability doesn't change from trial to trial. Then we say x is binomial in p if x equals the sum from I equals 1 to n of y sub I, where the y's are independent Bernoullis. So it counts the number of successful trials. That is, if we run 10 trials and 3 of them succeed, then x equals 3. Or if I flip a coin 5 times and I get 4 heads, then x equals 4. So what's the probability that x equals k? Well, for x to equal k, k must be between 0 and n. So I can either be successful on 0 of the trials or up to n of the trials, but I can't have a negative number of successes, and I also can't have more than n successes in n trials. For x to equal k, for a k between 0 and n, I need a p to the k, so I have a p to the k here because k of the trials were successful, and each succeeds with probability p. And I also have n minus k unsuccessful trials, so I have 1 minus p n minus k times. And then I need to have an n choose k because the trials could come in any order. So for example, if I run 3 trials and I want 1 success, my first trial could succeed and my second 2 could be failures, or I could have a failure and then a successful trial and then a failure, or my first 2 trials could fail and then the last one succeeds. So I need to count the ways I could have the event that I end up with k successful trials and different permutations. Okay, so this is what I was explaining. To have p, the probability of x equal k, exactly k of the n trials succeed. And to choose those k trials in which we're going to succeed, the number of ways is n choose k. And for the successful trials, the probability is p, so we get p to the k. And then for the other failures, which would be the other n minus k trials that fail, each one has a probability of 1 minus p. And to find the expected value of x, the easiest way is to use that formula that it's the sum from 1 to n of the yi's, where each y is just a Bernoulli. And so because we can bring the expected value inside of sums, this is just the sum from 1 to n of the expected value of the yi's, and the Bernoulli random variable has expected value p. So plugging that in, we get p plus p plus p n times. and therefore the expected value of a binomial np is just n times p. So if I flip a coin 3 times, and my success is a heads, so each head occurs with probability 1/2, then the expected number of heads I get is 3 times 1/2, or 3 halves, which we actually computed in the previous video. And the last one we're going to talk about is the Poisson, and that's a Poisson lambda. We have one parameter. So first let's motivate this with an example. Suppose that phone calls come in at a rate of 2 per hour, and we create a random variable that represents how many phone calls we'll get in the next hour. So of course it's going to be random, but on average we're getting about 2 per hour. So maybe we could think of it this way. Let's divide that next 2 hours into, or let's divide the next hour into 15-minute intervals. So in each of the 15-minute intervals, we'll count a trial successful if there is a phone call, and a failure if we get no phone calls. Since there are 2 per hour, it's a 1/2 chance that there's going to be no phone call in 15 minutes. Therefore, this probability we do get a phone call will be p equals 1/2, and we're running n trials, n equals 4, because we have 4 15-minute segments in an hour. But this doesn't count quite right, because if there are 2 phone calls in the same 15-minute intervals, then we've only counted it one time. We've counted it once as being successful. But we should have counted it twice because we had 2 phone calls. So we could chop up the intervals even further. That way maybe the 2 phone calls would come in different time intervals. Let's say that we chop up into, instead of into 5 15-minute intervals, we'll chop them up into 5-minute intervals. Then the probability we get a phone call is 1/6, and we have n trials. But it still could fail, because we could even get 2 phone calls within 5 minutes. So let's divide up time even further. Well, in both cases, n times p, the number of trials times the probability in each trial equals 2. And the probability is going to always decrease, because it's less likely if we have less time, but the number of trials is always going to increase. Because if we have smaller time intervals, we need more of them to get 1 hour. But their product has to be 2 all the time, because we always expect to get 2 phone calls. So, what's the probability we get k phone calls? Well, k has to be bigger than or equal to 0, because we can't get a negative number of phone calls. We could get 0 phone calls, but we could even get 1,000 phone calls if something crazy happens. So, we're going to have k bigger than or equal to 0. And we want to find the probability x equals k. And since n times p is always got to be the same number, we'll just call that lambda. Then, the probability x equals k, we're going to take the limit as n goes to infinity. So we want to keep chopping up time infinitely small. We're going to chop up the intervals to smaller and smaller and smaller time intervals. So we have the limit as n goes to infinity of n choose k, p to the k, times 1 minus p to the n minus k. And now we want to plug in these values. P is lambda over n, as we get from the formula we let np equal lambda. And n choose k is n factorial divided by k factorial times n minus k factorial. So this second line here is actually just plugging in those values for p and for n choose k. Now we have lambda to the k, and we also have a k factorial. Those things don't depend on n at all. So the terms that don't depend on n we can just pull out into the front here. And now we have the limit as n goes to infinity of n factorial divided by n to the k times n minus k factorial. And then 1 minus lambda over n to the n minus k. This first part of the product here, we actually have n values on top and n values on bottom. The n minus k factorial will cancel a bunch of the terms of the n factorial, and we'll be left with k terms on the top, but we also have k n's on the bottom. And as n goes to infinity, all of those terms will tend to 1. So this first fraction just goes to 1. And the second fraction may be something I do in class, but this limit's going to go to e to the minus lambda. So the probability x equals k is lambda to the k over k factorial e to the minus lambda. And that's just the definition for a Poisson. So that gives us kind of like an infinite refinement of the time intervals so that we don't end up accidentally counting a time interval as 1 even though we had 2 phone calls during that time interval. And we also can account for any number of phone calls that may occur during that time. So the probability x equals k is lambda to the k over k factorial e to the minus lambda for k bigger than or equal to 0. So no matter how many pieces we chopped this into, we were approximating this number of phone calls via binomial, right? So we always had binomial np, but the expected value at every step was np, which we called lambda. So the expected value at every step is always lambda. And if we take the limit as n goes to infinity, we actually preserve the expected value. That's something we're not going to show in our class, but for now, just take it as fact that even if I take the limit, the expected value doesn't change. So the Poisson random variable is going to have expected value lambda. Notice that once we get to the Poisson, to finally defining it, with dropping all this motivation, there's no n and p. There's only one parameter lambda. And that parameter lambda's got to be bigger than 0. And then the expected value of the Poisson is lambda, and you see the probability formula right there. All right, God bless, guys. I'll see you soon in class.